All right, everybody, welcome. Thank you so much for joining us for another Sky Tonight. My name is Andrea Decker, and I have the pleasure of working for the Fleet Science Center. As many of you know, because you're here, the first Wednesday of each month is Sky Tonight, a planetarium show at the Fleet Science Center. Normally, we host this at the Fleet Science Center in our beautiful Hycroft Dome Theater. Unfortunately, the building is still closed due to the pandemic, and so we thought before we miss out on all the space fun, we will bring this show online, and we've been happy to do so. Unfortunately, for a year now, we just remembered that the last live show happened this week, a year ago, Lisa, right?
Yes, last Sky Tonight show in person was last March.
Oh my God, it's
Yeah.
it's been a wild ride, people. But it's been great that you've joined us for so many of these events and that you're here tonight. And I hope you will continue to enjoy these events, either virtual, as long as we have to have them virtually, or hopefully sometime soon back in person at the Fleet Science Center. A couple of things before we get started. This is Zoom webinar, so your cameras or microphones do not work and the chat is disabled, but you can still engage with Lisa through the Q&A function. So at the bottom of your screen, you will see two speech bubbles with a Q&A underneath. When you click on that, it opens a window. You can type in your questions and send it to us. Lisa normally has kind of three sections to her talk. So she starts off with some news, space news, whatever is happening in the world regarding to space. And then she talks about the sky tonight. So she leads us through what the sky looks like if we were to go outside tonight. Maybe not, it's a little rainy. And then, of course, we're going to get to the topic of the talk tonight, which is planetary atmospheres. So if you have questions to either one of those, you can just type them anytime you want to. We might get to them in between those sections. If not, we'll look at them at the end for the Q&A for sure. And then we are recording this session, and it will be available at the Fleet Science Center YouTube channel in about a week or so. So you will be able to rewatch it and re-enjoy this if you like. And when we get to the Q&A, I'm going to share a audience survey, a little poll. So if you could take a minute to fill that out while you listen to the Q&A, that would be wonderful. We love to hear about our audience, who they are, where they're from, what they like, what they don't like. This way we can make sure that we provide you with the best program possible. All right, and I think that's about it. Lisa, want to take it away?
All right. Thank you so much. Let's see if I can get the screen shared.
By the way, for the people who are new, Lisa is the Fleet's wonderful resident astronomer, and she's also a professor of physics at the City College.
Yes. Thank you so much for the wonderful introduction. And I am once again very happy to be here with all of you. Although we hope to see you under the dome again soon. I miss you all having you there. All right. So we're going to start off by talking about some current events. One thing that's happening this month is the March equinox. And so this month marks the beginning of spring. It'll happen here on March 20th. And I say on March 20th here because the equinoxes and solstices take place around the same time every year within about a day or so. And for us, the equinox will be marked on March 20th, and when the sun on its path crosses what we call the celestial equator, which is the line that our equator would make on the sky. And so what you're seeing here is four different images of the Earth taken from space, so you get a really good perspective of what the angle of sunlight looks like on the solstices and equinoxes. And so the top left shows uh, the the December solstice. The top right is the March equinox. And so you can see the difference in angle in sunlight. And so that on the equinoxes, all parts of the earth are getting sunlight coming in at the same sort of angle, coming in level. And then and on the equinox, excuse me, on the solstices, you see the other extremes. And so, yes, we mark spring here in March. And once again, this image is hopefully helping you understand that it is the tilt of the earth and the angle of sunlight that is the reason for the seasons. All right, what is this weird image? This image is an image of Venus from the Parker Solar Probe during a Venus flyby from last summer. Those streaks that you see are actually cosmic rays, which are particles actually hitting the detector. But the Parker Solar Probe is flying around the sun. It's orbiting the sun to get great images, but it changes its approach to the sun by doing some gravitational flybys of Venus. And so you're seeing here cosmic rays hitting the detector, but you're also seeing the atmosphere of Venus. And I wanted to mention that, and we'll come back to the atmosphere of Venus later in the talk when we talk about planetary atmospheres specifically. And then update about supernova 1987A. Supernova 1987A occurred in 1987, but one of the things that makes it the most interesting is that it happened in a nearby galaxy in the Large Magellanic Cloud, which is a galaxy that actually orbits our own galaxy. And it is the closest supernova that's happened in sort of what you might want to call the age of telescopes, since the Hubble Space Telescope and other large space telescopes have been launched. And so, what we've been waiting for since 1987 was to see what this supernova left behind. Did it leave behind a black hole? Did it leave behind a neutron star? And there is evidence from several telescopes now that have led to doing this simulation that shows what it appears to have left behind is a neutron star. And so this is the first evidence that we've had so far that this is a neutron star formed in the heart of supernova 1987A, which is amazing when you also think about it, in that this would be the youngest neutron star than we have ever been able to observe in terms of knowing when it was formed. And so hopefully we'll get a lot more interesting data from this. And then there's been a lot about Mars in the news, but I'm going to wait to talk about that later when I can show you where Mars is in the sky. So, this is just a few of the interesting current events in astronomy. Now, let's take you on a tour of the nighttime sky. So this is the nighttime sky as set for San Diego at around 8 o'clock tonight. So if the sky clears up and cooperates, this is kind of what you would be able to see when you go outside. Except the stars are brighter here than you can see in a large metropolitan area like San Diego. To give you an idea of how to orient yourself on this, north is at the top of the screen, south is at the bottom of the screen, east is on the left, and west is to your right. So looking in the center of your screen, you're pretty much looking directly overhead. So that's kind of to give you an idea of what you'd be seeing up in the nighttime sky. And we like to start off our tour of the nighttime sky by, showing you the myths that are up on the sky. When we show you these images, they come from a catalog of 88 constellations that astronomers use. And these are the stories that you've always heard about in terms of what are constellations up on the sky. And so here are some of the names that go with these and we'll take a closer look at some of the individual constellations here. But when you go outside, you don't see the labels and you don't see the images. What you see are stars, and the human mind likes to connect the dots. And so when we do our sky tour, we're actually going to use the stick figures because it's more like what you'll be able to see when you go outside and look on the sky. And so here is the sky with the stick figures and the names. And some of these constellations you might have heard of, and some of them you may have not. So let's start with a constellation that, even if you haven't heard of it, you've heard of at least part of it. Ursa Major, the Big Bear, which is the home of the Big Dipper up in the northern part of the sky. And it is a huge constellation. It's one of the largest constellations. I believe it's the third largest of the 88 modern constellations on the sky. And what I find interesting about this particular constellation is that lots of cultures in the northern hemisphere that looked at this constellation saw it as a bear. And so it is a shape that has evoked the idea of a bear for many people for a long time. And I find that interesting because most of the constellations that we look at on the sky, I have no idea how people said, okay, that's a ram, right? But that multiple cultures saw this as a bear is something I've always found fascinating. And then we have some heroes up in the sky. This is Perseus. In Greek mythology, Perseus was the son of Danae. He was the hero known for several deeds. One of the things that he did was he slayed the Gorgon Medusa. So the mythical pictures of him often depict him carrying a Gorgon's head. And the most interesting star in this particular constellation is a star named Algol, which is a shortened for the name Raj Algol, which means demon star or head of the ogre. It is a interesting star because it is a variable star. But what we mean by variable star is it doesn't always emit the same, or we don't always see it as shining at the same brightness. This is a particular case where it's what we call an eclipsing binary. It's because what we're seeing up in the sky isn't one star, it's two stars, and we actually see them interfere with each other's light as we watch it on the sky. It's located about 93 light years away from our solar system. A light year is the distance that light travels in a year. And so if you're looking at a star that's 93 light years away, you're not seeing it as it is, but rather as it was 93 years ago. Another prominent constellation up in the wintertime sky is Auriga, the charioteer. The brightest star in Auriga is named Capella, and it is a star that if you have been outside this winter looking up at the sky, you have noticed it. It's bright enough to have caught your attention, and it's located about 42 light years away from our solar system. And what I find kind of interesting about this constellation is it is home to the galactic anticenter, which is a fancy way of saying is that if you want to look at the center of the galaxy, you look opposite Auriga. Like you're looking, when you're taking a look at the constellation Auriga, you're looking at the longest distance outward from our galaxy as opposed to looking inward. And so that kind of gives you a little bit of a idea of where we are in our galaxy because our solar system is not at the center of the Milky Way galaxy, but it's also not at the very edge. We're about halfway out. And so looking towards this part of the sky, we're looking outward from our outward or directly opposite the galactic center. Now, if you want to go look for the constellation Auriga, one way you can do it is go look for the constellation Orion, which is a more popular, very prominent constellation, and then look above his head. And that will take you towards Auriga. This is Orion the Hunter, though. Probably it is the most famous of the wintertime constellations, if not the most famous of all constellations. And why is it so famous? It's because it's big on the sky and it has lots of prominent bright stars. So you have the three stars of the belt. You have the bright bluish star down in his right foot called Rigel, which is about almost, it's between 700 and 800 light years from our solar system. And then you have the bright red star in the left shoulder, which is Betelgeuse, located about 400 or so light years from our solar system. Now, the thing about Betelgeuse is that that's the star that if my students say, "Hey, Dr. Will, what star is most likely to go supernova up in the sky that we can see next?" I would point towards Betelgeuse. And some of you might remember last year, Betelgeuse was in the news a lot because its brightness was fluctuating, and all the astronomers were like, "Please blow up, please blow up." But it's now back at pretty much its normal brightness. So, no exploding Betelgeuse, probably not yet, but we can hope. We can hope. Now, Orion the Hunter is accompanied up in the sky by his hunting dogs. We have Canis Minor, the small dog. The brightest star in Canis Minor is named Procyon, and it's located about 11 light years away from our solar system. And its name comes from a term that means before the dog because it rises before Sirius, the brightest star in Canis Major, which is the big dog. Now, Sirius is the brightest star visible in the evening sky from the Earth. It is the brightest star, other than the sun, that we see in our sky. And it's bright for a combination of reasons. It is both a a bright star. It is both hotter than our sun and a little bit bigger than our sun. So it emits more light than our sun does. And it's also relatively close, at only about 9 light years from our solar system. And so we have Canis Major and Canis Minor, Orion's hunting dogs, helping him hunt across the sky. But I always hypothesize that they really are going to get distracted and go after Lepus, the bunny rabbit, up on the sky. Because my dogs don't do anything remotely helpful. And so I can't imagine these dogs would have been helpful either. And this is an interesting case where, although Lepus was one of the 48 constellations in the catalog developed by the astronomer Ptolemy back in the second century AD, it doesn't appear to really represent any known bunny rabbit in any of the Greek or Roman myths that the other stories are attached to. Now, when I mentioned that constellation back from the second century, many of those 48 constellations are actually still in use today in the 88 constellations that astronomers use nowadays. And so that also gives you an idea of a couple of different things. That astronomy is an old science, that we have been cataloging stuff for literally thousands of years, and we have records of doing so. And then also that constellations don't change their shape greatly on the sky. It's another way that we know that. There haven't been a whole lot of bright supernovae happening nearby that take out visible stars, because when Betelgeuse explodes, it's going to change the shape of Orion. But these are constellations that we've been talking about that have held their shape for thousands of years. So it's just sort of an interesting way to interpret what we're seeing on the sky and how long lived it is. The brightest star in Lepus is actually fairly dim. It's not a very bright constellation. And one of the reasons why it's faint from our point of view is that it's over 1,300 light years from our solar system. Did you know there's a unicorn on the sky? There is a unicorn on the sky. It's the constellation Monoceros. Now, this one doesn't date back to the second century. It actually dates back to the 17th century. And what happened at that time was there was an astronomer that said, we have been using constellations that connect the dots between the bright stars, but that still leaves gaps in the sky. And for astronomers, we didn't just use constellations to express myths. We used them to catalog positions on the sky. And so if there were gaps in between the constellations, there were places where I would have difficulty communicating to you what area of the sky I was looking at. And so in the 17th century, there were attempts to basically uh, draw some constellations to fill in the gaps between the brighter stars. And so this is when we start to see some fainter constellations. And so none of the stars in Monoceros are easy to see with the naked eye, but it does have some beautiful deep sky objects that you can see with telescopes. Probably the most famous of which is the Rosette Nebula, because it looks like a rose. Um, and then we have this absolutely huge constellation rising over in the southeast right now, called Hydra, representing a sea serpent. It is actually the largest of the 88 modern constellations. And I think you can really notice in this one that there's not a whole lot of bright stars over there. In fact, the brightest star in Hydra's name is Alphard, which comes from a term that means solitary one, because it's all kind of the only bright star over in that part of the sky. And it is a star that's located about 175 light years from our solar system. And then this is a very faint constellation, one of those ones from the 17th century. It's named Sextans after the astronomical sextant. And so this one isn't named after a myth. This one is actually named for a piece of equipment. And we see that a couple times in modern constellations. There are some constellations visible from the southern hemisphere, telescopium and microscopium, that you get an idea that those are more modern constellations, although to an astronomer, a modern constellation is from the 17th century, right? So our definition of modern is a little bit different than a lot of people. And this is a constellation that once again covers sort of a very faint part of the sky. And then we have another faint constellation up in the sky tonight named Leo Minor. And you might be saying, Leo Minor? I thought it was just Leo. Well, that's because this is the small lion as opposed to the big lion on the sky. And so which brings us to the signs of the zodiac. So what we have here are the signs of the zodiac that are up in the sky tonight. Uh, with so we have Leo, Cancer, Gemini, Taurus, and Aries. And then what you'll notice is that there's a green line going through them. And if you look carefully, you can see months of the year next to that green line. And that's because that green line represents the solar ecliptic or the path of the sun on the sky. Now, we know that the sun, basically relative to the planets, remains fixed in our solar system. So, what we're actually seeing up here is where the sun appears on the sky due to our revolution around the sun. And so, because I have this set for 8 o'clock tonight and the sun set around 5 o'clock, you'll notice that March is below the western horizon. But the fact that the path of the sun travels through these constellations is why they gained cultural importance. These were the constellations that showed changes on the sky. And those changes also include the fact that the moon and the planets hang out over in this part of the sky as well. So let's take a look at some of the signs of the zodiac. Starting with Leo over along the eastern sky. Leo is the one that it actually is still a fairly bright constellation, easy to see even from a bright metropolitan area like San Diego. The way you go outside and look for it, you have sort of that backwards question mark marking the front of the lion. And then you have that triangle marking the tail of the lion in the back. All of those stars actually are visible from San Diego. So Leo pops out fairly clearly. The brightest star in Leo is the one at the base of that backwards question mark. Its name is Regulus, and it's located about 77 light years from our solar system. The next sign of the zodiac over to the west is Cancer, the crab. It is the faintest of all the zodiac constellations. In fact, you and I would have difficulty going outside and looking for it tonight. Basically, if we were outside looking for it, I would tell you to look for it based to the west of Leo in terms of trying to figure out where to find it on the sky. Now, you might be wondering what crab would this be? That is up on the sky. It is a crab that fought against Hercules when he was fighting the Hydra. Hercules killed the crab after it bit him in the foot. But then the goddess Hera, who was not a fan of Hercules, or I guess Heracles in the Greek myths, put the crab up into the sky so that Heracles would be faced with it forever. And it was only after doing these sky tours that I realized how much of the sky myths are all about vengeance and irritating people. It's kind of, I don't know why, but it is. The next sign of the zodiac over to the west is Gemini, the twins. The two bright stars are named Castor and Pollux after famous twins from Roman mythology. And when you go outside, you take a look at this constellation, it is obvious why they're named twins because they really do look almost identical to each other on the sky, but they have nothing to do with each other. In fact, Castor is almost twice as far away from our solar system as Pollux is. But these two stars have evoked the idea of twins for a very long time. In fact, in Babylonian astronomy, this area of the sky was known as the Great Twins, or these stars were known as the Great Twins. And so that naming predates the Roman reference that now it has up on the sky. Then I'm going to skip a constellation and go to the last sign of the zodiac over in the western part of the sky, which is Aries, the ram. And this is the one, like, it just looks like a straight line of stars on the sky to me. And when you connect the dots between the brightest stars, this does not look like a ram to me. So if you're not seeing it, I don't see it either. That's okay. The brightest star in Aries is named Hamal, and it's located about 70 light years from our solar system. And so now let me go back to the final constellation I want to mention to us tonight, the last sign of the zodiac, and another famous one, the constellation Taurus, the bull. Now, this has a lot of bright objects for you to go look for in the sky. The bright red star that marks the eye of the bull is named Aldebaran. It's located about 65 light years from our solar system, and it's one of the brighter stars in the evening sky in the winter. And its name comes from a phrase that means follower because it's following this little cluster of stars, if you can see my mouse, hopefully, which is the Pleiades, named after the seven sisters from Greek mythology. And that is an example of what we call an open cluster of stars. It's a young cluster of stars. It is the second closest open cluster to our solar system. And when we talk about open cluster, they are relatively young. Now, in astronomy terms, that means millions of years, not billions of years. But they have recently been formed from our point of view. Now, the closest open cluster to our solar system is actually mostly hidden under the T in Taurus here. See this V that marks the face of the bull? That's the Hyades, which is another group of sisters from Greek mythology. And it looks like Aldebaran is a part of that group because it lines up so nicely in the V. Has nothing to do with them. It's not a part of them. It's just a line of sight thing. But the reason why I wanted to finish our sky tour with Taurus tonight is because Mars is in it. And so right near the Pleiades. And so let's talk about Mars for a few minutes. I am way too excited about Mars right now. I could go on for a long time about Mars, but let's talk about why Mars has been so prominent in the news recently. This is an image of China's Tianwen-1 spacecraft, which entered orbit around Mars this month. And it marks the first successful Mars mission from the Chinese National Space Administration. And it is not just an orbiter, it does have a rover on it, and they are going to attempt to land a rover later this spring. And so we wish them luck with that. And not only did China have their first successful mission to Mars this past month, but so did the United Arab Emirates. This is an image from the Hope Mars mission, the first interplanetary mission from the United Arab Emirates. And so we also congratulate them on getting this spacecraft to Mars. But the one that you probably heard about most in the news was the arrival of the Mars 2020 mission, which included the Perseverance rover. Now, for those of you who were here last month, I showed you this graphic showing you the different stages that were going to happen, which is pretty much identical to when Curiosity landed several years ago, the same technology with the parachute, excuse me, the heat shield, the parachute, and then the sky crane doing the powered descent to the ground. What was different about this mission is they had cameras on all the pieces and they took images. And I'm not going to show you the video because I would just end up playing that video for you for like the next 40 minutes. But this is one of the images taken of the rover while it's still in flight. And so this is taken from above, basically the descent vehicle looking down at the rover. The streaks that you're seeing on the ground is actually dust kicked up by the landing jets or the jets on the descent stage because they have to slow down the rover so it can land and not crash, right? We want a controlled landing here. Now, the thing with Mars is it has an atmosphere. So we use a parachute to slow down the speed of the spacecraft somewhat, but the atmosphere isn't dense enough for it to slow it down enough. And so that's why we have to also use the sky crane to get these really heavy vehicles down. Perseverance, much like Curiosity, it's about the size of an SUV. For the Spirit and Opportunity rovers, they didn't have to do the sky crane part, because they weren't heavy enough. Speaking of parachutes, what you're seeing over on the right is the parachute. While the Perseverance rover was landing, the Mars Reconnaissance Orbiter was watching. And so this is an image of the parachute while the spacecraft was landing, taken from about 400 miles away. And so the Mars Reconnaissance Orbiter team got this for Curiosity too. So I was really hoping they would get it again this time. And so after the spacecraft landed, the rover landed, it started taking some images, and you might notice that this gray image, it looks a little bit fuzzy, and that's because these first images were still taken with dust covers on the lens. But you'll notice up in the top of the screen, you see sort of this plume. That's where the sky crane landed. Because after the sky crane drops the spacecraft down so that it doesn't actually land on top of the rover, it just put on the ground, it actually kind of jumps away. And so what we're seeing here is the plume from the impact of the sky crane landing, which is just really kind of amazing to see. And then just earlier today, this set of images was released. The rover has been spending the last week basically checking out all of its equipment. And so now it is not just taking a few images, but now it's moving. And so science will be able to start. Its scientific mission will be able to start. And then I did want to show one of the images, beautiful, beautiful images that have come back so far. A really interesting area geologically because this is an area of Mars that looks like it was once maybe a river delta. This is an area on Mars which may have had water at one point in its past. And the color of the sky is because of the Martian atmosphere. And so uh, I wanted our topic for the rest of the night is to talk about planetary atmospheres. And so I wanted to show you a picture of one that recently taken from a new rover. But before I continue on, I just wanted to make sure, did we have any questions I should address from this part?
Yes, we did, and it's perfect timing actually, because the first question is about perseverance. And Colleen is wondering, is there anything that has already been shared from the mission that you've been surprised by, or has everything been as expected so far? And she would also like to know, besides the astrobiology angle that Perseverance is going for, is there anything else you're hoping it might discover or bring new information on?
Those are some really great questions. Sometimes I think when we look at images of Mars, we're just like, oh, yeah, that looks like Mars. I mean, that my first reaction was like, oh, yeah, that's definitely Mars. Because we're there often enough now to know what it looks like, and it seems really familiar to us. When we go to Mars, oftentimes we're looking for how the history of water on Mars and its path and whether or not like the astrobiology angle, whether or not there has ever been life. But I always find it fascinating that when we are looking at stuff on Mars, we are basically testing our hypotheses that we understand how things work on Earth because we're landing in a place that looks like it has been carved out at least partially on one side of this large crater, Jezero crater. On one part of it looks like a dried up river delta. You can kind of see this fan of where water used to flow. And for us, we do that by comparative planetology, which is a fancy way of saying, oh, it looks like that on Earth. I bet it's caused by that same thing on this other planet. And so now we have to test it. So you can go there. It's one of the reasons why it's great to send rovers because they can now go around this planet and this small area of the planet, but still go around and pick up different samples. And so I love the geology. If I hadn't been an astro major, I probably would have been a geology major. It's my one of my loves. And I also hope we keep finding more meteorites. The Opportunity rover found a couple of meteorites on Mars. And so it's just kind of fun to see those big chunks. They're so obviously meteorites out in the middle of the Martian terrain. And so, yeah, I just look forward to whatever we get. The mission's only been on the ground for a week now, and science results haven't started really coming back yet. They were doing a press conference earlier today, and that was mostly to release the images of the motions that they're actually getting ready to start the science. So I will keep you updated here for anything that happens on the Mars mission because Mars, I feel really geeky about it.
Me too. And we have one more question, and then
Mhm.
we're going to look at the atmospheres of other planets too. The question is, when there was water on Mars, is there any idea what the atmospheric pressure was as at its peak? I can't speak tonight, sorry. What the atmospheric
It's
pressure
okay.
was as at its peak.
So I can't think of it off the top of my head, but I'll mention it later tonight that right now the atmospheric pressure on Mars is less than 1% the atmospheric pressure here on Earth. So to have water on Mars, the atmospheric pressure would have had to have been higher. And when I say water, I'm actually specifically meaning liquid water. I'll show you Mars has water, but it's in ice form right now, right? Ice form and vapor. So it's in gas phase or solid phase, but is it in the liquid phase? And we do have evidence, and I'll show you more later, why we think it did have liquid Mars, liquid Mars, liquid water abundantly on the surface earlier on. So all I can say was it would have had to have been significantly higher. So think of the Earth, our atmospheric pressure is about 150 times higher than that of Mars. So it would have had to have been significantly higher. And let's see why some of that is. So we're going to be talking about planetary atmosphere. So here is our solar system to scale. James O'Donoghue does these really wonderful to scale models of the solar system, really great graphics. So I wanted to use this one here. And what you'll notice here is that Mercury, Venus, Earth, and Mars, the four terrestrial planets, are pretty much right on top of each other on this scale. We are all really close to the sun. And then Jupiter, Saturn, Uranus, and Neptune, the other four planets, are much further out from the sun. And we're going to ignore Pluto for this evening. We're going to talk about planets. Don't get me started. And then I wanted to show this to you because, as you might imagine, our distance from the sun does play a role in whether or not we have an atmosphere and what that atmosphere behaves like. It also determines whether or not liquid water can be stable at the surface. And this brings us to the idea of habitable zones, or sometimes you might hear these referred to as the Goldilocks zones. Not too hot, not too cold, but just right for what? Liquid water to possibly be stable at the surface. So, what you're seeing on this graphic is that for hotter stars, blue stars, or for cooler stars, red stars, and then we have a sun-like star, the location of the habitable zone, which is shaded in green, changes. The hotter the star, the further away the habitable zone is. That makes sense. Now, here we argued not too hot, not too cold, but just right. And so our Earth is in the habitable zone of our sun. And Mars and Venus are just to the outskirts on either side. You also might notice here the idea of being 1 to 2 times the size of the Earth. You need two things to be a habitable planet. You need to be at the right distance for liquid water to be stable, and you have to have an atmosphere, not too much, not too little, but have it be just right. So in our solar system, one of the things then, as you might imagine, in terms of the habitable zones, uh, that distance from the sun might also determine the amount of atmosphere or might play a role in the amount of atmosphere that we have. And so here we see the planets and Pluto also as a function of temperature, not distance exactly. You might notice it's pretty close to being the same as distance, except there's one outlier. Venus up here is hotter than Mercury, although Mercury is closer to the sun. And so we'll have to figure out why that is. But otherwise, the other planets in the solar system actually are marked by distance from the sun. And you'll see here that the temperatures of Jupiter, Saturn, Uranus, and Neptune, they are much colder than we are here on Earth. And that actually does dramatically affect the type of atmospheres they have and how much. And so here are the four Jovian planets, Jupiter, Saturn, Uranus, and Neptune. And they're often referred to as gas giants. Uranus and Neptune sometimes are referred to as ice giants because of the materials that they can contain inside their atmospheres. And what you'll notice here, though, is that they are dramatically different looking than Mars, than the Earth. And their atmospheres are slightly different than what you and I think of it as an atmosphere, because for you and I, our definition of an atmosphere is based on our experience. It's this ocean of air that we swim through every day. On the Jovian planets, they are gaseous or compressed fluids down to a rocky core in their centers. They're not a thin layer of atmosphere above a mostly rocky planet. So when we talk about their atmospheres, we're talking about their cloud layers at the very tops. All four of these planets are mostly hydrogen and helium, and what gives them their different colors are the subtle differences in their atmospheric compositions in their outer layers. The clouds that we're seeing and the sort of yellow orangey colors that we're seeing for Jupiter and Saturn, we have ammonia and ammonium hydrosulfide clouds that give those sort of colors. There's also some water ice clouds too. Whereas the blue and bluish green colors of Uranus and Neptune come from methane. They have a higher percentage of methane, and because it's colder out at that distance, methane can condense in the atmosphere more readily than it can for Jupiter and Saturn, even though they also have methane in their atmospheres. And so we'll talk about methane again in a few moments because methane is a good greenhouse gas, which means it absorbs infrared, but it also is good at absorbing red, which means it reflects back more blue, which is why Uranus and Neptune have their more distinctly bluish greenish colors. So their atmospheres are not what we normally think of as planetary atmospheres. You're used to thinking of atmospheres like the Earth or for the terrestrial planets. And so here are the four terrestrial planets. We have Mercury, Venus, Earth, and Mars, and they're all here to scale with each other. So you get the idea that Venus and the Earth are very similar to each other. Mercury and Mars are kind of similar to each other, but Mars has an atmosphere, Mercury does not. And that's because Mercury is so close to the sun that its combination of low gravity and the high speeds that the particles would be going to because they'd be heated up due to proximity of the sun, it doesn't allow basically, the gravity of Mercury doesn't allow it to grab on and hold to an atmosphere, or if it formed with one, it did not allow it to keep it. But Venus, Earth, and Mars all have atmospheres, and therefore they have distinct climate and weather. And so I mentioned those words, so I do want to come up with some definitions for us really quick. So, weather versus climate. We often hear them used interchangeably, but they are not the same thing. Weather refers to atmospheric conditions that occur locally and over short periods of time. So, like that thunderstorm today here in San Diego, which completely freaked out one of my dogs, that's weather, not climate. And this image taken from space, looking down at the Earth, that bright flash is a thunderstorm going on. And so you can see how localized it is. And that's what we mean by localized weather. So, what's climate? Climate refers to long term and regional or even global average values of quantities like temperature and humidity and rainfall. So, long term and large scale. And so that's the difference between climate and weather. And then the difference between global warming and climate change, two terms that you often hear about interchangeably. Climate change refers to a broad range of phenomenon due to global warming. And so sea level rise, loss of sea ice, extreme weather events, those are climate change due to global warming, where global warming is a more specific term that is solely talking about upward temperature trends that we have been noticing across the entire Earth. And so we'll see a little bit more about that in a bit. So, what's going on here, and why am I mentioning global warming now before talking about, say, Venus? Well, because for the three terrestrial planets that do have atmospheres, we can explain the conditions of their atmosphere currently by understanding the greenhouse effect, because the greenhouse effect is in play on Venus, Earth, and Mars. And so here is a graphic talking about the greenhouse effect for here on Earth. Sunlight comes through our atmosphere and it heats up the surface of the Earth. And you know that the surface of the Earth heat re-radiates that back in infrared in heat, because you have probably at some point made the unfortunate experimental mistake of walking outside in bare feet during the summer, and your feet know that the surface of the earth is re-radiating a lot of that light back as infrared, and that infrared light gets absorbed and re-emitted in all directions, helping to warm our atmosphere, and it gets absorbed and re-emitted by what we call greenhouse gases. Now, a greenhouse gas is meant to evoke a greenhouse, the idea that it is humid and warmer than the outside conditions. And that's because water is the most dominant greenhouse gas in our atmosphere, followed by carbon dioxide. And then in extremely tiny amounts in our atmosphere currently, nitrous oxide and methane. Methane is also a greenhouse gas. And so these are the greenhouse gases in our atmosphere. And so water vapor currently is the most prevalent greenhouse gas in our atmosphere. But then what do we got going on with Venus and Mars? Well, Venus has an atmosphere that is almost 97% carbon dioxide, and then to about 3.5% nitrogen. And it does have water vapor in its atmosphere in trace amounts. Recent studies actually show that the surface of Venus may have had water on it for about 3 billion years or so of its lifetime, and that the conditions on Venus now are due to something we call the runaway greenhouse effect. So you're seeing a couple of different images here. The image on the left is from Mariner 10 from back in the 70s, and it's visible light, and you can see that Venus has such dense, thick cloud layers that we actually can't see the surface of Venus in visible light. And then the image on the right is a composite visible light image on the left, infrared image on the right, and taken over one of its poles from the European Space Agency's Venus Express spacecraft. And I like showing this one because it really gives you a feel of the circulation of the atmosphere and the amount of infrared light in it. And so Venus has been heated up greatly due to something we call the runaway greenhouse effect, which is when the greenhouse effect gets out of balance to the point where water vapor and carbon dioxide outgassed up into the atmosphere, taking the oceans up with it. Because while there were oceans on the surface of Venus, that would have been its biggest sink of carbon dioxide. That's one of the reasons why we worry about the oceans here on Earth evaporating, because they don't just evaporate up water, but it's where a lot of our CO2 is also currently held. And so we think Venus was always too close to the sun. Remember that Goldilocks effect, right? The habitable zone. Venus was always too close to the sun for water to probably have been completely stable on the surface. So its water cycle would have always been a little bit out of balance, more evaporation than precipitation. And so we think all of the what we would call volatiles, the water on the surface of Venus, would have now gone up into its atmosphere, taking the carbon dioxide with it. And why does that matter? Here are some images of the surface of Venus from the old Soviet Union Venera spacecraft. And what you're seeing here is really dry dirt. And what is it like there? Well, this spacecraft didn't last very long because Venus's atmosphere is 90 times the atmospheric pressure of the Earth because of all of the volatiles being evaporated up. And that atmospheric pressure combined with the fact that the winds circulate very efficiently means that the temperature of the at the poles is about the same as the temperature at the equator. The temperature on the night side of Venus is about the same as the temperature of the day side of Venus, and the temperature makes it hotter than Mercury because that's how efficient the greenhouse effect is. It that all so though that Venus is almost twice as far away from the sun as Mercury is, it's actually hotter due to the runaway greenhouse effect occurring. And so this is a set of images from the Akatsuki spacecraft from the Japanese Space Agency showing you the cloud motion and Venus. Now from Venus, we'll head to Mars. And what we're seeing here in this image, the left-hand image is Mars, taken by the Mars Global Surveyor spacecraft many years ago. You can see a ice cap down in the southern region. You can see clouds above the tops of the volcanoes in the center of the image. And then on the right-hand side is an artist representation of what Mars may have looked like in the past when there was more water on liquid water on its surface. And so you might be wondering, why do we think that there's was a long history of water on the surface? Well, first of all, that you can see the southern cap in this image, and then here's an image of the north polar cap. Mars's polar caps are seasonal; they get bigger and smaller with the seasons, and so we know that they have some water ice in them as well as carbon dioxide ice. Here is an image of water ice in Korolev crater on Mars. And so when you see this much ice in one area, it looks like a pool of ice basically liquefied. This looks like a lake in a crater in a crater that that was liquid at some point and then turned into ice. And then what we really see all over Mars are regions that are often called channels. Some of them look like they're long meandering uh, channels that were carved out by rivers being on the surface for long periods of times. And then we also see outflow channels, which would have been cases where maybe catastrophic flow from flooding of some sort. But we see geologic features all over the surface of Mars that look like would have been, if they had been on Earth, we would have said, oh, they were carved out by water. And then we see water up in the clouds. This is one of my favorite images from the Opportunity rover because you see the sand dunes on the ground and then the water vapor clouds up in the sky. So what's up with the atmosphere of Mars? Well, Mars's atmosphere is also mostly carbon dioxide. It's over 95% carbon dioxide. But the problem is that we think due to the reverse greenhouse effect. Remember, Mars is so far from the sun, we think it was always too cold, and that the rate of precipitation was faster than the rate of evaporation. So we think a lot of Mars's ancient atmosphere precipitated out and is locked up as permafrost or ice in the ground. And so Mars has a thick blanket of atmosphere, now less than 1% the atmospheric pressure of the Earth. And we can estimate it should be that way due to the greenhouse effect. Because when we saw that image of all the terrestrial planets, and to scale with the sun and the Jovian planets, we saw that the terrestrial planets were all pretty much right next to each other. So we think they formed at the same time out of the same stuff, and they should have had very similar atmospheres. So why is the Earth so different than Venus and Mars? Or for the moon, for that matter. Here's an image taken by a spacecraft, a snapshot of the Earth and the moon in the same image. And the difference between the Earth and the moon is that the Earth has an atmosphere and the moon doesn't. And the reason why the moon doesn't is that its gravity is not strong enough to hold on to an atmosphere. But that's the difference. I love the contrast. That's the difference that having an atmosphere makes. And so our atmosphere helps us have a moderate temperature here on the Earth. At our distance from the sun, if we did not have an atmosphere, our average temperature all over the surface of the Earth would be well below freezing. And so it is the greenhouse gases in our atmosphere absorbing and re-emitting infrared radiation that means that we have a nice average temperature in the mid 60s all over the entire planet. And so the greenhouse effect would seem like it's a good thing. And I would say it is, but like so many things in life, it's a good thing in moderation, right? And so the reason why we are concerned is this graph, which shows atmospheric carbon dioxide levels over the course of the past almost 500,000 years. And you can see that where we are today is at a carbon dioxide level much higher than we have ever been. More greenhouse gas, the hotter the temperature, the more you evaporate up the, the basically we don't want to be Venus. We don't want the water cycle to get out of balance, and we so that we evaporate up more than we precipitate back out. So the question is this happening? Are we seeing the right data? And so here is a set of what we call temperature anomaly data um, from over the last almost century and a half now, taken from different research centers all over the earth. And you can see our data matches. And so this isn't one research group saying that the earth is getting hotter. This is everyone seeing data that the earth is getting hotter. Then we have this interesting graphic. Temperatures from 1880 to 2017. And once again, we're looking at something that they call a temperature anomaly, which means how far above or below an average are you getting? And so red, orange, and yellow are hotter than the long time average. Blue is cooler than the long time average. And now let's take a look at what happened starting in the 70s. You'll notice the color of the screen suddenly got very, very different. And in the last couple of decades, if you think it's been warmer, it has been. So here in the United States, you'll notice this map that says temperature change since 1970. These temperatures are in Fahrenheit. You will notice that don't get fooled by the ones that are in a lighter color. That means there's only been a temperature change of 1.5 degrees Fahrenheit. So everywhere in the United States has gotten warmer since 1970, most dramatically Alaska. So, how does that correlate to greenhouse gases? Well, here are the greenhouse gas emissions for the United States. Mostly carbon dioxide and then methane are the big ones. And then where do they come from? Electricity dominates, but you'll notice the 12% there is commercial and residential. So it depends on, I shouldn't say it depends. When you take a look at this data, you need to realize that individuals are a small part of it, and then large corporations or large industries and transportation make a much bigger bulk than individual sources. And then how has that affected us? in 2018, this is a map for 2018 that showed a number of what they called billion-dollar disasters. And so each of these event caused over $1 billion in damage. And what we've been seeing here in California have been wildfires, the increase in wildfires, the huge and huge wildfire damage. So you might be interested, for those of you local here to San Diego, what are considered to be the top climate hazards here in San Diego? And what we see here are the top 5 compared to in 2050, where they think the big concerns are going to be in 2050 to where they are currently, with some sort of arcane index that they use. But sea level rise is a big concern here in San Diego, and then ocean chemistry comes next, and then warming and water deficit and drought. But the different temperatures affecting the temperature of the water, the temperature of the oceans is changing the chemistry of the ocean, which has an impact on fishing and fisheries and so on out in the water. So I just thought I would talk to you about that sort of local impact. And then if you want to connect it, it's those local impacts that help you connect climate to to stuff with immediate relevance. Um, Wildfires, drought storms, agricultural changes, disease movement, and so on. And so if you're talking to people in your life about climate change, and so on, you can actually point to things that are occurring currently that are due to climatary impacts. And we know that the greenhouse effect works here on Earth the way that it does because we can compare ourselves to Venus and we can compare ourselves to Mars and explain all 3 of our atmospheres by the greenhouse effect. So that's just a quick tour of the planetary atmospheres of the solar system with a focus on the terrestrial planets and the greenhouse effect. So if you have any questions for me, now would be the time,
They sure
and I'd
do. We
love
have
to
some
answer them for you.
questions. Yay.
All right. And then let me know if you want me to stop sharing the screen.
Yeah, that would be good.
Okay.
Thank you, my
Do
dear.
that.
Okay,
There
well,
we
before
go.
I'm going to read the first question, I'm going to pull up the poll because otherwise I forget. That happens. Okay, so we launched the poll. There's your
Okay, there's the
chance to
poll.
give us some data. We all love data. You know, we're in science. Data is the best.
Data.
Okay, so the first question, do you know of any proposals for probing a planet's atmosphere with a probe suspended by a balloon or blimp?
Not off the top of my head, but there's a couple of interesting missions coming up. So the Perseverance rover that just landed on Mars. Some of you may have heard about the helicopter on it named Ingenuity, or Jenny for short. So that is going to be our first attempt to do powered flight in an atmosphere of another world. So the only goal for that one is to test it. It's sort of like an engineering proof of concept. They're not depending on it working. But there is another mission called Dragonfly, which will be launched later this decade, and it will be going to Titan, which is the largest moon of Saturn, which has an atmosphere. And that one is going to be a combination rover slash helicopter, which is it will land and it will do some research and then it'll fly away and it'll land somewhere else and do some research. And so it'll, instead of driving between location to location, it will actually fly. So that one, I'm really interested in that one. And a lot of work on that one is being done by Malin Space Science Systems from here in San Diego County, who also makes a lot of those cameras that take the beautiful images on these spacecraft that we've been showing you.
So we have a fun question, which I'm always fascinated about, right? We're going to Mars, we're going to the moon, maybe we're going to live there, which brings up the question of changing a planet's atmosphere, kind of terraforming, basically. So the
Right.
question is, if greenhouse gases can do that, then why don't we just blast Mars's atmosphere with methane?
So that's a great question. And so it's always interesting to think about, can we actually terraform or alter the atmospheres on a large scale? Because obviously we can, because life has altered atmosphere here on Earth at large scales, and it has for a long time. In fact, we think the oxygen in our atmosphere is we think we're already living in a secondary atmosphere, that we're not living in the atmosphere that we were formed with, because this oxygen in our atmosphere was likely put there by biological organisms outgassing it, because we don't see this much oxygen on other planets. So, can I take a bunch of methane or other efficient greenhouse gases to Mars and dump it on Mars and get a better an atmosphere? Well, the difficulty with that is that Mars gravity is about one third the gravity of the Earth, and so its escape velocity, we call it, the speed that an object needs to go to leave the gravitational influence of a world, is significantly less than the Earth's. And so, if I'm going to dump light particles like gas molecules, methane molecules, the question is, how do I slow them down enough so that Mars holds on to them? Because basically having the equivalent of smokestacks of methane, that stuff's just going to fly away. And so one of the ideas I've seen thrown around is that maybe you throw a comet at Mars, the impact partially liquefies the water, leaving some behind, and then it can slowly evaporate up, thickening the atmosphere of Mars. But we're talking like you got to have like a couple thousand years of patience. Nothing reasonable will happen quickly.
Nothing quick. Well, there goes the living on Mars theory in the next couple of years.
Yep,
With an atmosphere. I mean, we could
with
still
an
live.
atmosphere.
Yes. Next question is, how does the sun give light to Earth and then Earth gives it to the moon?
So the sun gives light to both the Earth and the moon. Occasionally we do see, okay, so when we take a look at the moon up in the sky, we're seeing it shine predominantly by reflected sunlight. Just like in the image behind me, we're seeing the Earth shining by reflected sunlight in this image. Do we occasionally see the moon shining by reflected Earth light? Yes, we call it Earth shine. And so, have you ever gone outside at night and you've seen the crescent moon, but you feel like your eyes can fill in the rest of the moon around it and you can barely see the moon? That is the moon shining by reflected light, sunlight off the earth. That's why we call that earth shine. But when we show you images of the planets in the solar system in visible light, it's all in reflected sunlight.
Thank you. Next question is, when did we land a craft on Venus? Did we and
So we
when?
landed, the Venera spacecrafts landed back in the mid late 70s, maybe 1980 at the latest. And because of the inhospitable pressure cooker conditions, they lasted less than an hour. So like those images that you're seeing were taken before the spacecraft stopped. Venus is not a friendly place and to try to land, because the temperature on the surface is over 800 degrees Fahrenheit and it's 90 times the atmospheric pressure of the Earth. So it is a pressure cooker. And so, yeah, not landing there likely again anytime soon, unfortunately. But whatever spacecraft we would send would have to be awfully sturdy, which would mean heavy, which means more expensive and harder to get off the ground.
Yeah. Pressure cooker, that's a great analogy. I like that one a
And
lot.
yeah.
Next question is, how do we know if the planets outside the solar system have atmosphere?
Ooh, now that's a fascinating question. For a couple of cases, we have detected atmospheres of other planets around other stars. And it's usually when they're doing something called transiting their star. What do I mean by that? You know how sometimes the moon eclipses the sun, it crosses in front of the sun from our point of view. Well, if a planet crosses in front of a star from our point of view, we can actually detect whether or not it has an atmosphere from when the atmosphere first starts to go over the star versus when the planet fully covers it. And so, in a couple of cases, we have been lucky enough to get chemical traces of basically spectroscopy by comparing the star's spectrum, its chemical signature, to the chemical signature it has right when the planet is starting to transit in front of it. And that's how we can say very definitively in some cases, oh yeah, that's a Jovian style planet with this much hydrogen, etc. But only in a couple cases so far.
Fascinating though, it's amazing.
Yes.
And we have a question: if the greenhouse effect continues on Earth in its current trend, will the Earth's atmosphere get heavier?
Absolutely. Hi, Lisa. Absolutely. So on Earth, if the runaway greenhouse effect occurs here on Earth and the oceans evaporate up, taking all the water and all the carbon dioxide up in it, we actually estimate that the atmospheric pressure here would be 70 times what it is currently.
Whoa,
Yes. Yeah.
that would be a lot too.
Right.
That
And
will
so
bear me
that's the
down.
exactly. Well, that's one of the things I like to point out is that when we're talking, I think sometimes people think global warming is just a couple degrees. It'll just be a little hotter. But no, we're talking huge, drastic impacts down the road. And one of the reasons why we refer to the runaway greenhouse effect as the runaway is that once it starts, we won't be able to stop it.
So have we reached that point of no return?
I don't know. It's the climate models. Scientists, no one likes to think about it this way, but scientists are often conservative by nature. And what I mean by that is we don't like to make predictions stronger than what we really think the data shows. And so we are currently where climate models had us like 20 years down the road. Because scientists like to underestimate impacts, if anything, to make safe. I don't want to say safe, but to know that their predictions fit are not exaggerated, right? And so, yeah, it's been looking pretty grim. That's all I'll say.
Well,
Yeah,
something good for us to think about for sure.
it is. And it's a reason why some of the stuff needs to be addressed quickly because the time to deal with it appears to be shortening. That's what
Yeah.
I'll say. Yeah.
Okay, I've got a fun question for you in between. Mary is wondering, what's your favorite space movie?
Space movie. What's my favorite space movie? Like, does it have to make sense, a space movie, or just fun space movie? I think in many ways, I've always loved 2010. Not 2001, but 2010. You'll notice that they don't have any sound in space. It's soundtrack and the realism of like the way they wandered in space. I've also enjoyed The Expanse, the TV show, in terms of the way it's depicted space.
Yeah, that's one of my
And
favorites
then
right now.
yeah, and I enjoyed the movie Gravity because it was almost more of a love letter to what the Earth looks like from orbit.
Yeah,
Not necessarily the story, but just like I was just enjoying watching the Earth from orbit for a couple of hours. That was a gorgeous movie.
that's awesome. Yeah, I agree with that. So we have three more questions I think we can take. Oh, actually, we have a couple more. So we're already a little bit over time. So Lisa, you can pick two more questions. I'll leave that to you.
All right, so let me just scroll and see if I can combine any of them at all.
Yeah, that's why I
When did the
let you
first
do that, because I think you know better which ones you can combine and which not.
Okay. So when did the first craft land on another planet with an atmosphere, Venus or Mars? I believe we landed on Mars before Venus, but they were both would have been in the 70s. When there was water flowing on Mars, was the sun different than it was now? Not significantly. The sun would have started off cooler and then think of the sun as like your car engine. It starts off cold and then it heats up, but the sun has been at its operating temperature for quite some time. So that's not going to be the dominating factor. Why is there an upward limit on the size of a planet to maintain an atmosphere? Because if the gravity is too high, you can actually accumulate too much gas and then suddenly you're like a Jovian planet, right? So it's bigger. What was the asteroid name that hit the Earth that made the dinosaurs die? The asteroid didn't necessarily have a name, but we call it the Chicxulub impact event because of where it landed in over the Yucatan Peninsula. And then how far does our habitable zone extend into the solar system? So basically, the habitable zone in our solar system runs from about Venus to Mars. And it's just that we're pretty much like in the midst of it. So we're solidly in the habitable zone, but it actually it's a band. And Venus's atmosphere, it was just a little bit too hot, and then Mars was just a little bit too cold.
So do we measure the habitable zone just by temperature, basically?
Yes, because we start off by the criteria is at what distances can liquid water be stable, and then you have to actually roughly say like, okay, but can the planet actually hold on to it? Then so we start off by distance from the star, determining temperature, and then there's the other factors like planet size and so on, and whether or not it has an atmosphere.
Well, thank you so much, Lisa, for another amazing talk. I just
Thank
learn so much
you.
every time we do these. It's fascinating, really. Thank you so very
Yes,
much. And thank you, audience, for joining us tonight. We're always so glad to have you with us. We get excited that you're here when we do these, and we do these for you. If you weren't here, we wouldn't be doing this. So there's that. And with that, I want to wish you a wonderful rest of the week and stay safe and stay healthy, everybody. Thank you so much.
yeah. Good night. See you next month.
Bye, everybody.
Good night. Bye.